Hey guys, today I'm going to present a solution to Chinese National Olympiad 2019 problem 3. Firstly, let's take a look at the problem statement. We define S as a set of size 35. A set F of mappings from S to itself is called to be satisfying P of K if for all x and y in S there are some functions, not necessarily different, f1 to fk in F, such that fk of fk minus 1, so on, up to f1 of x equals fk of fk minus 1 dot 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 of f1 of y. We are asked to find the least positive integer n such that if f satisfies the property p of 2019, then it must also satisfy the property p of n. So to solve this problem, we are going to introduce the notion of distance. So for all x and y of the set S, we define d of xy to be some number r, where r is minimal such that there are functions f1 up to fr in big F such that fr of dot f1 of x equals fr of f1 of y. We make the following observation, which is immediately implied by this definition. For some pair of x and y where x is not equal to y and they're both elements of f, we have that there exists an f in big F such that d of x comma y is exactly equal to d of f of x comma f of y plus 1. For all the other f in F, this value must be more than or equal to d of xy minus 1, because otherwise this distance would be lower. So from that fact, it follows that if for x not equal to y in S, we have d of x comma y equal to r, then for all s less than or equal to r, and of course 0 must also be less than or equal to s, there are x prime and y prime in S with distance x prime, y prime equal to s. Because from this we have r minus 1, and then we can iterate this until we reach the value of distance 0. So we also want to note that f satisfies p of 2019. Therefore, d of x comma y is an integer less than or equal to 2019 for all pairs x comma y in S. This is not the case for all sets f, because it is possible to construct it in such a way that it is impossible to find any functions fr to fn such that this equality holds. Therefore, d of x comma y may be undefined for some pairs x comma y for certain definitions of f. But in our case, we don't have that problem due to f satisfying 2019. Therefore, we can make the following observation using what we got in the last line. The set d of x comma y for x not equal to y in S is exactly equal to the set 1, 2, dot 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 up to n, where n is just the number which we want to evaluate, since in the minimal case at least, which we are investigating right now, since n is the maximal value of d of x comma y here. But we can use this equality to bound m from below, since n is the size of set 1, 2, up to m, which is exactly equal to the size of set d of x comma y for x not equal to y, both in S, which is less than or equal to the size of the set x comma y for x not equal to y, both in S, because d of x comma y may be equal for different pairs, therefore we have this inequality, but this cannot be lower. But the value of this can be computed because it is the size of S, which is 35, all over 2. This is the binomial coefficient. So what we now know is that if f satisfies P of 2019, then it must also satisfy P of 35 over 2, which is equal to 595. Therefore, n is less than or equal to 35 over 2. We will construct an example which shows that m is exactly equal to this value. To do that, we let s be equal to the set 0, 1, comma, up to 35, and big F equal to the function f, which sends x to x plus 1 mod 35. Hence, 0 is sent to 1, 1 to 2, and so on, but 34, f of 34 is equal to 0. And additionally, g such that g of 0 is equal to 1, and g of x equal to x for x not equal to 0. We can already see that this f satisfies P of 2019, which is quite trivial because we can always increment both x and y until, for instance, x equals 0, then we increment x by 1, and so on. Then the difference between y minus x will decrease over time, and we will be done in at most 2019 steps like this, about 1200 or something like that at most, using this strategy. So now I claim that d of 1, 18 is equal to 35 over 2. Proving that will suffice to prove our statement that m is equal to 35 over 2, because this implies that m must be greater than or equal to 35 over 2 in this case. So how do we do this? There are basically two strategies, one of which I've already described to you, to make these two values equal using many of these functions fk up to f1. The first one is to apply the function g each time x hits the value 0, and the other strategy is to use g whenever y is equal to 0. So there is no better way than doing this. For instance, if we used f when one of the values was equal to 0, then we would just skip one turn and end up where we were 35 turns ago. On the other hand, if we sometimes applied g to increment x and sometimes to increment y, then we would do nothing in terms of changing the difference between x and y, which is no good either. So there are essentially two cases, and we will evaluate the number of steps needed in each case, and the minimum of both of those will be our answer for d of 1, 18. So in the first case, we will increment 1. This means that d of 1, 18 is less than or equal to d of 0, 17 plus 34. We have applied f 34 times right now. This is again less than or equal to d of 1, 17 plus 35. We repeat this process multiple times to obtain that this is less than or equal to d of 1, 1 plus 35 multiplied with 18 minus 1, but since d of 1, 1 is 0, 1 is equal to 1, this is exactly equal to 35 over 2. So we now know that using our first strategy we can reach equilibrium for 1 and 18 using 35 over 2 functions. So d of 1, 18 is less than or equal to 35 over 2. Now let's consider the second case, where we will increment the value of y. So d of 1, 18 is less than or equal to d of 18, 0 plus 17. We have applied f 17 times. This is then less than or equal to d of 18, 1 plus 18. But we can already finish here, because from now on this strategy is going to be symmetric to the first one, just with the difference that x and y are swapped. So we are going to get the value of 35 over 2 for 18, 1 plus 18, which is higher than 35 over 2. So we know that out of these two strategies, the better one is the first one, which gives the value the equality after 35 over 2 steps. We have already figured out that there is no better strategy than either the first or the second one, and therefore d of 1, 18 is exactly equal to 35 over 2. And since f satisfies P of 2019, but it does not satisfy P of 35 over 2 minus 1 due to d of 1, 18 being equal to 35 over 2, we get the value for m of 35 over 2. And we are done.